Continuing in this section, which was, what was it, 13.3, we just did arc length. Now I want to define something called the arc length function. So the definition of arc length function, we're going to say let C be a smooth curve defined by R of t on some interval. Okay, that's pretty standard. Then the arc length function is really just S of t equal to the integral from a to t. So you're not defining the endpoint like you're going, your starting point's defined, but your endpoint's not. And it's used in a couple different ways to define other things. It is a magnitude, so this is just arc length, r prime, magnitude r prime of t, or I'm sorry, not t, you put it in your dummy variable there, of u du. So this is called, so S is called the arc length function or arc length parameter. So arc length parameter or function. So graphically speaking, it's like saying you have a curve in 3D that traces this thing out. I'm trying to use this thing on the side, see if it helps better. Everything's just right there. So your R of t traces out the curve like this. And then you could say it would start, maybe suppose, at R of a. And then you want to find that length from here to, well, we don't know. So we're going to say t. So that'd be your t. So so a is fixed, t is your variable. So not going to get too much into it, but it's used to define what's called curvature a little later. So just kind of keep this in mind. If you differentiate this, you get ds dt is equal to the magnitude of r prime of t. So that's the rate of change of arc length with respect to a variable, with respect to length. So we're going to use these concepts to talk about stuff a little later. So let's continue. So let's suppose you have some graph like that, and then you have R of t traces out the curve C. Then if you do R prime, you get the tangent line like this, so that's R prime. Okay, and then what we want to do actually is we're going to make that a unit vector. So we're going to make this into just a unit vector here. And so what do we do to make that a unit vector? And then I'll tell you what that is. We're going to call that t. Oops, I'm trying to use this thing. Okay, so we're going to define this now. So the definition of the unit tangent vector is t of t, capital T of t, and it's a vector. You take r prime, which is tangent to the curve. So you take r prime of t, and then you make it a unit vector. So how do you make it a unit vector? You divide by its magnitude. So keep in mind that then that unit vector has a constant length of 1. Okay, so this would imply a constant length of 1. That's going to have implications for other stuff later. Okay. Okay. Next definition has to do with that. What we define next is called the unit normal vector, or principal unit normal vector. So this is called the principal unit normal vector. So that you take in, or sorry, it's called in. So you take that vector in, and what you do is you take t, whatever t is, and then do the same thing. You take its derivative and then divide by magnitude. So the principal unit normal vector, you take the derivative of t and then divide by the magnitude. So it's normalized, again, because you divide by magnitude. So that's called the principal unit normal vector, and has an interesting property of what goes on. So the property says, and we're definitely going to prove this, says basically the unit tangent vector, t, and the principal unit normal vector, n, are always perpendicular to each other. And it makes sense to say perpendicular just because we're in 3D, really. Although you define it to be orthogonal is fine too, but they're perpendicular. So what that means then is we have the other vector. So you have n is going to look like this. So these are perpendicular, and its unit and its length 1. So that it will always be pointing in like that. And then this will be a right angle. So keep in mind to show this proof that the unit tangent vector is always length 1, meaning it's always constant. And we did a theorem that states if the magnitude of a vector is constant and you look at their dot products, you get 0. So check this out. All right, so from the past, okay, so recall, I don't know what section it was. Last couple chapters or sections we did this. Recall that if magnitude, if magnitude of r of t is constant, so it normally changes, right? I mean, as you trace around a curve, you could guess or picture so as you're tracing around a curve, you could picture that the tangent vector changes length as it goes around. So at some point it might be right here, and then another point it might be like it's almost like the velocity is changing depending on what the function is telling you to do. Okay. But if it is constant, then you get this result. So then, this is something we had already done. I'm just rewriting it really, so it's right here. Then r prime is orthogonal to r of t for all t and r. So that's long as if it's always constant, or it could be on a closed interval or something. But okay, but so then, if you look at a proof for that, let's see. Okay, so C proof. So C proof. I'm not sure where that is. I'm going to say above in my notes, but it's up there. I'll maybe in the next video I'll look it up. But you basically do the magnitude squared equals c, and then you do the dot product. Which when you do the dot product and you differentiate both sides, you get the dot product equal to 0. So we did do that proof already. So this is the arguments you have for t and n. So for t and n, we know that that the magnitude of t is 1 or always constant. Okay, so thus we know t dot n is basically magnitude t, or I'm sorry, t dot t over, or t prime over magnitude t prime. Well, if you, this is dot product. If you look at this, then you end up with, so this dot product is 0. So you factor this out, you get just this dot product is 0 because length is always the same. I'm kind of showing a little bit of the proof as how you would do it. So that's 1 over magnitude t prime, and then you end up with t dot t prime. Yes, well, t dot t prime is 0. So the whole thing is 0. Because n, see how, remember how n is defined? Right? N is defined to be this. And then if you have constant length, which you do for t, right? Magnitude of t is always 1. So this thing here is always 1. Or just, so if that's the case, then this is always going to be 0. Okay. Didn't explain that too well, but think about it. It's not that bad. You'll get it. So what that means then is you get this vector. So you get this curve like this, and then you have a vector t that might look like that. So there's your t, and then your normal vector is always going to be traced out like this, and that's your n, and then that'll be at right angles all the time. So that'll as you trace it out, you always have this and this being traced out. And it becomes, if you want to look this up, you should look this up. This is called the TNB frame. And so basically B, you just do, I will get to B later, but you do the cross product between T and N, and you get that normal vector like this, and that's your B. And then you make it a unit vector. You got to divide by its magnitude, and then so that's called a TNB frame. So and there's some animations of that. I'll see about posting and all that, but we'll get to that later. So we also get then is this concept that the acceleration vector, which might look like that, it always points on the inside. So our acceleration vector a of t is made up of, let me erase that, is made up of the components of, just gotta go a little further. So it's made up of these components of t and n. So it's a scalar that scales n plus a scalar that scales t, and that equals a of t. So it's a of t is basically something times t plus another thing times n. So we call that a linear combination. So a linear combination of t and n. Okay. So let me define that. So that's important enough to define. So let's define, so definition of a linear combination. This comes up a lot. Let U and V be vectors in R3, or it doesn't really matter, Rn, R3. And then we're going to say let R and S be just constants in the reals. Then the vector W, so if we can make W equal to a constant times U plus another constant times V, then that is a linear combination. That's how we define it, is a linear combination of U and V. So if you can write it like that, that's W. So notice then that if you can write a vector like that, then that would imply the same plane. So this thing here, we would say is same plane for U and V. So if you have U and V, here's your U and here's your V. Those have to, and then your W is a linear combination of those. There's no way to make it like pop out of the page here. So this W can't be that. That's just not going to work. W is going to be in the same plane. So it's going to be something like this where it's the same plane. So you can't add a scalar. A scalar is just going to stretch or shrink that, right? It's going to stretch this, or it's going to shrink that, or make it go this direction. But it's not going to make it pop out of the page when you add it up. So same plane is the critical idea, and we're going to see basically a proof of that. So there's a theorem that we will show, and I'll go ahead and do this in another video to kind of break it up a little bit. Yeah, we're going to show that A of t lies in the same plane as t and n. And we will do that by showing that A can be written as a linear combination of t and n, always.